Okay, so welcome. So we're going to talk about inductance today. And let me just get my timer going. Good. Okay. So we've done that if we have a current in a wire, it can cause a magnetic field. Let's do this the right way around. So if I have a current flowing through a wire, I can make a magnetic field. And we've also done that if our magnetic field through a wire loop changes in time, from Faraday's law, E equals minus n d phi by dt. So these two guys kind of like mean that, man, I'm going to get these magnetic effects around current carrying wires. And when I get changes in the current through those current carrying wires, then I'm going to get Faraday's law effects. I'm going to get EMFs produced, etc. And there's two situations where this becomes really significant. One is when you have big currents, and so the big magnetic fields, and so things happen a lot. And the other one is when you get fast changes. And what comes to my mind certainly is at the substation, at those little substations in the housing districts. Those handle really big currents. I mean, every house can draw 100 amps, maybe 200 amps on a newer house, and there's however many those houses, those things feed. So a tremendous current. Now we don't all draw current at the same time, but potentially it's all there. And especially after there's been a blackout. When there's a blackout, people try to turn the lights on to see if, and so they tend to leave them on. And so suddenly everything wants power when you try and turn the thing back on. And so there's a massive surge of current, a massive current and a massive surge. And so what you find is you couldn't have a switch that just turned on New York City. It just wouldn't work. Induction effects would fight you and close you down or delay you. And so the trick with big current applications is you turn it on one bit at a time. In the end, it can all be energized, but you don't want to energize it all at once. You don't want to start energizing it all at once, because there's big currents, and no matter what the time scale is, there's big currents. The other thing that comes to mind is at the other extreme, actually, and that's in a computer. In a computer, you have very little current flowing in a computer for the most part. There's quite a lot of power dissipated in a computer. So it's not that it's like no current flowing through it, but the signals are really small. But the signals change really quickly. So if I have a stream of data, it's basically how quickly I can go from a 0 to a 1 and back again determines my speed. And if it turns out that because of induction effects, that very sharp edge is going to lead to an effect which is then going to slow me down, then I quickly get into the stage where I have huge problems because my signal is being just messed with by these magnetic effects. And the signal itself is not very big, but the timing is very precise. And so I get caught out there as well. So there's two circumstances in which inadvertently these magnetic effects in circuits are going to be problematic. But then there's going the other way. And you could turn around and say the same thing happens with capacitance to some extent. When I have wires next to each other, there's a certain capacitance. If I have any kind of plate near another plate, there's a certain amount of capacitance. There's stray capacitances around, and most of the time you don't care because it's such a small effect. But every now and then you can imagine it will be an issue. Same with these magnetic effects. Most of the time it doesn't matter. I don't worry about it in an application like in this room. But when I go to the extremes, it matters. Well, with capacitance we found actually there were certain physics that arose when we made a capacitor. And we actually made attempts to make capacitors as big as possible. You know, we wanted big capacitors for maybe storing energy. That's a possibility. But more commonly for processing signals, either as a timing device or as a filtering device for signals. We found that a capacitor was a high-pass filter. That meant high-frequency changes tend to not see the capacitor, but to a low-frequency change, the capacitor is very evident and very problematic. Well, can we do the same with a magnetic effect? And we can, in fact. We can actually deliberately get little pieces of wire and wind them into a coil and actually even put a piece of iron inside. And they sell these things. Sometimes they encapsulate them, sometimes they don't. And they sell these things as inductors. It's got a symbol L. And those are used deliberately in circuits. You can introduce an induction into a circuit. And the idea again is maybe you could use it as some kind of storage device for energy, but you know, it wouldn't store much energy and not for very long. But really its value is that it's used as a low pass filter. So the capacitor cuts out your low frequency and lets your high frequencies pass through, and an inductor cuts out your high frequencies, lets your low frequencies pass through. They're like the antithesis of each other. And you might think, well, okay, then you never want both of them together because the capacitor will kill you at low frequencies and the inductor will kill you at high frequencies. So what's left? Well, what's left is the bit in the middle. And you could call the combination a band pass filter. And that's actually the principle behind tuning networks, which we'll get to not in this chapter but the one after. In tuning networks, you set your capacitor so that you reject the lower frequencies, and you set your inductor so that you reject the higher frequencies. And what's left, that sweet spot in the middle, that's what gets through. And that can be, for example, the frequency that your radio station, of the radio station that you want to listen to. And when you turn the knob on an old-fashioned radio, typically you're changing a variable capacitor. As simple as that. So that's where we're headed. So let's look at inductors. What we can say is when the current flowing around a circuit changes, then the circuit induces a back EMF on itself. So we can have circuits messing with themselves. When a solenoid is used as a component in a circuit, is called an inductor and is particularly significant for high frequency current changes. It kills you at high frequencies. And inductors called transient effects, like we saw with capacitors, where it takes a certain time. We can't say charge up because the inductors don't get charged up. Really, we should say energized. So it takes a certain time to create the magnetic field inside the inductor, to energize it, and it takes a certain time to collapse that magnetic field to de-energize it. And that could be used for a timing effect. So that's the places where we're going. We're going to look at basically self-induction to begin with. So imagine this circuit. Imagine I close the switch. And let's have a look. That's a battery, so the current comes out of the positive and goes around the circuit. There's my current flow. And we know that, you know, if we have a wire that's carrying a current and I have a current in that direction, I use the right-hand rule. So I put my thumb pointing along where the eye is, and I let my right-hand fingers curl around. And what I see is my right-hand fingers will point into the page on that side and come out of the page on that side. Can you see that? So if I look at this guy, then I see that, oh, I get into the page on that side and out of the page on that side. And the same would be over here, into the page and 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 into the page. And I see all the magnetic flux lines caused by this natural flow of current are into the page on the inside of the loop, and they'll all be out of the page on the outside. I don't particularly care about the outside, you know, but that's the pattern that I see. Well, before I closed the switch, there were no flux lines into the page inside the loop, and now there are. So that sets me up for Faraday's law. And basically with Faraday's law, what happens is I say, well, okay, we didn't used to have a current, we didn't used to have this flux line. I want to get rid of it, so I'm going to cancel that out. 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 So this is what the circuit says is, we used to have none of these flux lines, and now you've made all these flux lines, so I'm going to do what it takes to cancel out the change. And again, if I look at Faraday, if I look at my current thing, and I know if my current is in the opposite direction, then that's into the page, and that's out of the page. So we're just, sorry, that's into the page. The X is into the page, and the dot is out of the page. And so what I see is, oh, I can create these purple flux lines by having my current flow that way. So you see immediately the current that I'm inducing is fighting the current that the battery is producing. And I can actually figuratively represent this by saying, oh, there's going to be a imagined EMF source. It doesn't exist. It's as if that source was there. And I'm going to call that, because it's pushing back, I'm going to call that the back EMF. And so I see that I've got this fight going on between the circuit as it is and the circuit, the effect on the circuit caused by Lenz's law. That I'm not going to let you change is Lenz's law. So we say when the switch is closed, the current driven by the battery increases in time. The magnetic flux through the circuit loop due to its increasing current also increases in time. So the magnetic flux going through that loop increases in time. This increasing flux creates a back EMF because of Lenz's law. The EMF has the sense, that means the direction, that creates a current, that creates a magnetic field, that opposes the change in the magnetic flux. So the source of the EMF is opposed to the induced EMF, and current increases gradually. These two fight each other. Eventually the battery is going to win. But Lenz's law is going to make it win in time, not instantly. And this is called self-induction. You're inducing a back EMF in your own circuit. And so it's sometimes called a back EMF. Okay, so let's think about this self-induction. So here's my power supply. This is variable, it doesn't matter. Here's my power supply. I suppose I could vary that power supply, or I could have a switch that I'm closing. There's my inductor. There's always a little bit of resistance in a circuit. So sometimes, for theory's sake, we want to ignore the resistance, but by and large there is a resistance. So it's good to account for it. And basically, also the symbol for inductor is like a helix. And then it's got a symbol L. And I'm using the international system symbol for a resistor here. In America we'd say that. And then we say when current is flowing through the solenoid, when the current flowing through the solenoid changes, a back EMF is established. The back EMF is always proportional to di by dt. It's the rate of change of current with respect to time. And I'm sorry, this should be a subscript L. I think it is a subscript L. I think the subscript is just such a big letter. So the EMF is equal to minus n d phi b by dt. Whose law is that? What law is that? We did Faraday's law. And then we say Faraday's law, well, the EMF is equal to minus L di by dt. We decided that. We defined L to be that. L is called the inductance. So we say that the induced EMF is equal to minus L di by dt. It's a bit like V equals IR. We have our current bit and we have it multiplied by some constant, which we call resistance. This is a bit like that. We have di by dt and it multiplied by a constant, which is like the inductance bit. Okay. L is called the inductance of the solenoid. The inductance is a measure of the resistance to the changing current flow. So if I actually look at an inductor, I can say what's its physical so I'm not there yet, I'm sorry. So then, okay, I can define this L, and L is equal to n phi b over I. N phi b over I. And we get that from, if you look at this, let's have a look. Well, no, I can't get it out of there. No, I can't get it out of there, I'm sorry. So L equals n phi b over I. I is the current. N is the number of turns. And phi b is the magnetic flux going through it. The SI unit for inductance is the Henry. And Henry is 1 volt second over amp. It's a named unit, which tends to hide what it means. So from this page, I'd like you to be comfortable with that and that. Okay. Magnetic field of a solenoid is B is equal to mu naught N over D times I. We saw that. We did that in lab. We did that using Ampere's rule, I think. Yeah. Magnetic flux through each turn is phi b equals the magnetic field times the area of each turn. And this equals, well, mu naught N over D times I times A. We're multiplying that B, that's B. And just multiply it by A. If we remember that L is equal to N phi B over I, that came from the page before. L equals N phi B over I from that second equation. Then what we can say is that this is equal to, we have mu naught, what went on here? So, I've got to put my thinking cap on here. Let's have a look. So what they're doing is they're substituting in that B. I'm sorry, I'm just having a mind spasm here. So phi B equals that, which is that. So they're taking, they're taking that guy in for that. So we get N over I. And then we go, so we take those two together, and then we have N squared, and we have A, and we have the I's cancel, so we get mu naught N squared A over D. I just noticed that negative sign there, and I'm not sure where that negative sign comes from at the minute. Okay. Well, L is equal to mu naught, rather than big N, which is the number of turns. We can get the number of turns per unit length and simply multiply it by the length. So it's ND squared over D times A. And so we get mu naught little n squared, the d squared, one of them cancels out with the d times a, and a times d, a times d is the volume. So we get L is equal to mu naught, number of turns per unit length squared, times v. I don't need you to know that. That's just know what the letters stand for. I don't need you to know that. I need you to know those two, but I don't need you to know that one. Okay? Just have a look at it. So the bigger the volume, so that means an inductor that's like that can have the same inductance as an inductor that's like that, as long as they have the same volume. You know, that's kind of interesting. If you somehow change the number of turns per unit length, if you double the number of turns per unit length, you don't have twice the effect, you have 4 times the effect. So a really tightly wound inductor with very narrow wire is very effective, as opposed to a loosely wound inductor. So, okay. So know your expression for your EMF in terms of your inductance, and know the expression for inductance in terms of flux and current and the like. And then let's go to this bit. So this circuit is basically a battery that's connected across a LR combination with a switch. If I leave this middle link open, so it's just like it's not there, and I close this switch, then suddenly current flows around my circuit. And I'm going to get an increase in current, which is going to cause inductance to take place. So I can say, well, what will my current flow be at any given instant? Now, if I think about this, then this looks an awful lot like I had with a capacitor. What's happening? So the capacitor, let's just remind ourselves, it said Q at any given time was equal to the maximum charge. And the maximum charge was, remember, it was the EMF times the capacitance, charge equals VC, modified by 1 minus e to the minus t over tau. And that tau, in this case, the time constant, was RC. Remember that from your capacitance studies? This is playing the same game, although we're not looking at charge now. We're looking at current. So your current at a given instant is equal to the maximum I. That's your maximum current. And I get that from Ohm's law. You know, V equals IR, I equals V over R. So that's my maximum current, modified by 1 minus e to the minus t over tau. And now, in this case, tau is equal to L over R. So tau equaled RC, tau equaled L over R. Rather than maximum charge, we have maximum current. So it's very similar. And for de-energizing, I would equal maximum, just not 1 minus, it's just e to the minus t over L over R. So it's very similar. And this time constant, of course, is the time to get to 63%. That's how long it takes to get to that. It's a way of scaling this effect. So what we say is, using Kirchhoff's rules, we get this equation. It's a differential equation, and the solution is, there's the solution. Boom. So remember the solution for the energizing. And I think if you remember for the energizing, you can figure it out for the de-energizing. It's just whatever gives you the opposite. Rather than 1 minus this exponent term, it's just the exponent term. But the rest is the same. Okay? And the way you de-energize is what you do is, having this, you open this and you close that, and then you can just allow the field inside the inductor to collapse. So we start off, let's have a look at this. We start off with basically no current when you close that switch, and then it takes time for the current to build up so that you are fully energized. Yep. Takes time for that to happen. And when you're at maximum current, then your V will be all across there, and you'll have no field across there, and vice versa. Like we did for the capacitor, where is it, etc. A little bit of a conceptual question, let's play with this. So I have two circuits, similar in design, except they've got different component values. Which one of these circuits, the red circuit or the blue circuit, contains the bigger inductor? Really, I should say the bigger inductor resistor combination, but let's just assume the resistors are the same, so I'm just comparing inductors for inductors. Which has the bigger inductor? Would it be, so what's going on here? I'm closing the switch, and at some point I'm opening the switch. So that's what I'm doing. I'm no potential, but even no current, and then I'm closing the switch so current can flow. I'm applying my battery's voltage, my EMF, and then at some point I'm opening the switch, so now there's no voltage applied. So which would be the circuit with the bigger inductor? Everything else kept the same. Would it be the blue one, or would it be the red one? So decide. You're right. Why do you think it's red?
Because it's taking longer to charge.
Yes,
Discharge.
that's right. Remember that this inductor is fighting you. If you have no inductance, you basically just go to the current and you stay at the current and you go off again. That's with no inductance. But the fact that you got inductance means that I'm going to fight this change, and the bigger the inductor, the more it fights. And so, yeah, the red one will be the bigger inductor between those two. What is the time constant of the circuit that consists of a 5 Henry inductor? So this is 5 Henrys, and a 9 ohm resistor. So I say my L is equal to 5 Henry, my R is equal to 9 ohms. My tau, which is my time constant, is equal to, what was it? It was L over R, wasn't it? So that equals simply, let's have a look. It's going to be 5 over 9. Man, what a choice. 5 9s are 45 seconds. So 0.555555 seconds. I'm just trying to think if there's a way that I can remember which way round this time constant is. If I had an LR series combination and I made L bigger, I would expect a longer, slower process, because it's the inductors that's slowing you down. So putting the L on the top for the time constant kind of makes sense. I guess the question is, why is R underneath rather than being on top? What's the effect of my resistance? My resistance determines the maximum value. So my I max is equal to my EMF over R. Everybody okay with that from Ohm's law? You see where that comes from? You know, we said delta V is equal to IR, and delta V in this case is equal to my electromotive force, my EMF, so I'm just substituting, then rearranging, yeah? So if you like, if this is I, and there's, well, if this is I and this is time, then the bigger the R, the smaller the I max. Yeah? So if R is big, there's my I max. If R is small, so this is R big and R small. You can see that? Yeah? And then the inductance determines how quick you get there. So to some extent, this is real hand waving. This is like, I'm really hand waving. But can you see how, you know, to go to this, my inductor takes a certain length, and and here my inductor takes a certain length. And what am I trying to say here? I'm trying to say, if I have a bigger resistance, I have a smaller I max, and so I expect less time is needed to get there. And so for the time constant, R should be on the bottom. I don't know if I'm just, you know, it's not rigorous, but, you know, it's that kind of makes some sense. Either way, you got to know it. L bin on top makes a lot of sense. R bin underneath makes some sense, but it's not squared away for me. Consider a circuit that consists of a 2-volt battery, a 4 Henry inductor, and a 7 ohm resistor. That are connected in series. What current flows through the resistor? I'm not going to say 30 seconds because I know already there's a problem with that. If I say tau is equal to L over R, then in this case my L is 4 and my R is 7, which equals 5 7s are 35, carry 5, 7 7s are 49. That's about 0.6 seconds. And I'm asking for 30 seconds. That's way too long. That's going to be full current. Can I make this, do you mind if I make this 0.3 seconds just to make it a bit more interesting, yeah? So then I say, well, my I at a given time is equal to my maximum current. What's my maximum current? What will determine my maximum current? What will it be? It's going to be my Ohm's law. Use your Ohm's law. It's going to be my EMF over my R. Yeah, there's my maximum current. But it's modified, and I'm energizing. So for energizing, it's 1 minus e to the minus t over tau. That comes out of the differential equation. So IT is equal to E over R, 1 minus e to the minus t over L over R. Now let's put some numbers in. So this is going to be my EMF is 2, my resistance is 7. 1 minus e to the minus t, well, for the t I want 0.3 over L over R, 4 over 7. And I get my calculator. These are always a bit of a pain to do, so you've got to do them somewhat carefully. I'm going to say, well, that's like 0.3 times 7, enter, divided by 4, enter. So I get about 0.5 for that. And then I'm going to go second e to the x, little negative, not the subtraction, but the little negative second answer. And I get 0.59. I go 1 minus second answer, and I get 0.4 times 2 enter divided by 7 enter, and I'm going to get 0.117 amps. And this compares with a maximum value 2 divided by 7 is equal to 2.8, so the I max equals 0.29 amps. So if I was to picture this, then that's 0.29, and my answer here was round about 10, 20, 30. And so this is my value, and that came after 0.3 seconds. And this other value, this 2.9, is going to come, my time constant, the 66%, which would be round about there, would be after about 0.6 seconds. Yeah, so that looks like that. So it makes sense. Makes sense in terms of this is my I in amps, and this is my T in seconds, and this is 0.6 seconds. And okay, cool. So if you got the skill for the capacitor, it's the same skill. It's just learning another equation. It's a very similar equation. You just got a different time constant, and you got a different maximum value. Remember, with the capacitor, it was charge, and with this guy, it's current. So it's really worthwhile lay them down side by side so that you can see the contrast and compare them. Okay. On this next one, so we're basically creating an electric field, a magnetic field. With a capacitor, we tended to talk about charging and discharging, but really, that's not what it's about. That's how you make what it's about happen. What it's about is the electric field in a capacitor. So charging is creating the electric field, and discharging is dissipating the electric field. And for this, energizing is creating the magnetic field, and de-energizing is dissipating the magnetic field. But the energy is in the magnetic field, in this case, just like the energy was in the magnetic field, electric field capacitor. So we say a battery must do work against an inductor to establish an electric current. Part of the energy supplied to the battery appears as internal energy of the resistor. The remaining energy is stored in the magnetic field of the inductor. Yeah, they're going to get heat given off by the resistor. That energy is going to be dissipated, etc., etc. If we use Kirchhoff's rule, so this is a loop rule saying the EMF is equal to the potential, plus the potential difference is equal 0. So I have my EMF and I have my potential difference across the resistor, and my potential difference across the capacitor, across the inductor, and that sums to 0. And then I do a bit of math trickery. This should say multiplying both sides by I. That's what that's saying. We get I times I times the EMF minus I squared R minus Li di by dt equals 0. And then we say, well, the rate of change of energy is equal to the inductance times I times the rate of change of current. The total energy stored in the inductor can be obtained by integrating. So we integrate this. My total energy equals my integral of all my little bits of energy, which is Li di between 0 and I. L's a constant. L integral of I di, which is a half Li squared. Now I seem to recall that for the capacitor, what we did was we had Q and we had V, and we said that the energy is equal to the area under this graph, which was Q delta V. Remember that? And then we said, well, hold on, we know that Q is equal to delta VC. So we'd say, oh, well, that equals, oh, sorry, no, and because it's a triangle, because it's a triangle, it's a half. So because Q equals delta VC, we get 1/2 delta V squared C. And we can substitute the other way and say, well, okay, delta V equals Q over C, so that will be 1/2 Q squared over C. So we had those three expressions, 1/2 Q delta V, we had 1/2 delta V squared times C, and we had 1/2 times Q squared over C. And it seems to me that these are more similar. It's going to be 1/2. We've got the half in there. And then this is the inductor times the current squared. And the equivalent would be, it would be the, I suppose it would be 1 over the capacitance times the charge squared. But it's got a similar form. I guess it's as simple as that. It's got a similar form, yeah? So I can put it in my toolbox as it's going to be 1/2. So this would imply, well, I bet there's a graph somewhere I can do the same thing I did before with the graph. I just need to think about it a bit more. But know that equation. The rest, so let's look. So that equation's important. That equation's important. You can always figure out the other one. And those two. Okay? The rest is actually for background. Because, so what happens next is they say, well, supposing that we have two coils or two loops that are close by each other. So rather than the current in a loop creating a magnetic field which increases, which causes an induction in itself, let's say the current in the first loop causes a magnetic field that increases through a second loop, which causes a back EMF in the second loop. So rather than it all in one loop, now we have two loops, and one of them is the causer and the other one is the receiver. One's the primary, one's the secondary. How are they linked? They're magnetically linked. And this is called mutual inductance. And it's the basis of the transformer. And we get to the transformer. In the old book, they put the transformer after AC theory, which I always thought was a little bit, it's a bit wacky, but that's how they did it. And this is the justification for it. And all I really want you to know is that there's this thing called mutual inductance, and it's basically when the changing magnetic field in one coil causes a back EMF in the other. So when the magnetic flux through a current loop, circuit loop, varies because of a time varying current in a nearby circuit element, we refer to this as mutual inductance. So we cause the effect in the brown. I've got a loop and I cut it in two. I just basically had two loops and I cut the page in two, and I'm looking at, this is a cross section through the top bit, and here's a cross section through the bottom bit, and here's a cross section through the top bit, and here's a cross section through the bottom bit, you know. It's there and there and there and there. That's what I'm looking at. And we're just imagining we're varying the current through this blue loop, and that's causing this magnetic flux to change. It's not just causing the magnetic flux, the current does that, but the fact that we're changing that magnetic flux, that current in time means we're changing that magnetic flux. And that's like bringing the magnet forwards or further away. If we increase it, it's coming forwards. If we decrease it, it's going away. So, okay. So I got a changing flux through this brown coil. Changing flux through this brown coil means I get an EMF in this brown coil. Okay. So we say, consider two closely wound coils of wire. Coil 1 has N1 turns and 1 amp of current. It creates a magnetic field passing through coil 2. And coil 2 has N2 turns. And so we get this expression, M2, the mutual inductance in the second coil is equal to the number of turns in the second coil times the flux passing through the second coil over the current in the first. And the other way around as well. And so we get these. And I don't care about any of those. Okay? What you're going to find in the end is the ratio of the voltages is equal to the ratio of the turns. And we're going to get to that later on. Okay? We'll get to that later on. Okay. So know that if I can cause inductance in a single circuit on itself, I can surely cause inductance from one loop to another. So a little change now. So let's imagine that I have a capacitor and I put it in series with an inductor. And then let's imagine that I charge up the capacitor so that it's got energy on it. I take the battery away. I charge it up, take it away. So now the energy is in the capacitor. There's no switch, there's no nothing, there's just a circuit. The charges want to recombine through the circuit, so they go from being on the capacitor, say positive and negative, and then they're the other way around, and that's like you take a pendulum and you lift it and you let it go, and it goes high and low and high and low and high and low and high and low. So what happens with this is you charge up the capacitor one way, and then you discharge it and you charge it up the other way. And then you discharge it and you charge it up the other way, and it goes backwards and forwards. And when the capacitor is discharged, there's a lot of current, a changing current going through the magnet, through the coil, and so you get a lot of energy stored in the magnetic field. And when the thing is here and there's no current flowing because the capacitor is fully charged, then you get no current in your inductor, so there's no magnetic field there. So you're going from magnetic field in the capacitor, you're going from energy in the capacitor because of its electric field to energy in the inductor because of its magnetic field. And backwards and forwards and backwards and forwards. Just like we have gravitational potential, kinetic, gravitational potential, kinetic. It's the same, it's the mathematically it's the analogy. Pendulum has a frequency. It's got a natural frequency. So does this. There's a certain rate at which you want to go from all the energy being stored as magnetic and all the energy being stored as electrostatic. There's a certain rate. And if we can express a value for that, a equation for that, then we can start, we can actually do quite a lot with it, actually. But we're going to cheat. So we say assume the capacitor is fully charged, so initially all the energy is stored on the capacitor. When the switch is closed, there's no switch, so let's just imagine that. When the switch is closed, the capacitor discharges through the inductor. A current flows through the inductor. current reaches its maximum value as the capacitor becomes fully discharged. At this point, no energy is stored in the capacitor, and all the energy is stored in the inductor. You might think it stops there, but the current flow continues at a slower and slower rate as the capacitor becomes charged in the opposite polarity. Eventually, the capacitor is fully charged and the current flow is zero. At this point, all the energy is stored in the capacitor again. So, you get these oscillations taking place, and these oscillations will have a natural frequency. And the natural frequency is in here. And you don't need to repeat any of this. It's just, if you're interested, we say that our energy is equal to the energy of our inductor plus the energy of our capacitor, which is a half Li squared plus a half Q squared over C. And so I can put those in. That's the same thing. Theoretical circuit has no resistance, so no energy is lost to heat. Rate of change of energy with respect to time equals 0. We learned that in physics 1, isolated system, no friction, no loss of energy. So du by dt is going to equal 0, which equals d by dt of a half Li squared plus 1 half Q squared over C. And then I'm playing some mathematical games, and basically what I do is I say, I'm going to split that I into I times I. I'm going to split that Q into Q times Q, and that's so that I can get a form that I recognize. I get L over 2 d by dt of I times I plus 1 over 2c d by dt of Q times Q. And I go, well, that's L over 2I di by dt plus di by dt times I plus 1 over 2c q dq by dt plus dq by dt times Q. And then I start combining things. Du by dt is equal to 2L over 2I di by dt plus 2 over 2c q dq by dt, which equals Li di by dt plus q over c dq by dt. And if I remember that my rate of change of energy with respect to time equals 0, and that my current equals dq by dt, and that my di by dt equals d2q by dt squared, that's a bit of just differential stuff. Then we get du by dt equals Li d2q by dt squared plus q over ci. Divide by I get this guy. And if I rearrange, I get d2q by dt squared equals minus q over lc. And I can write that as minus 1 over lc times q. d2q by dt squared is some function of q. Let's turn over the page. That's where I'm at. d2q by dt squared equals some function of q. And I look at that and I go, well, that's a differential equation. It looks a bit like the differential equation I saw before in mechanics. I don't remember it, but you can look it back up. Where I got d2q over dt squared equals minus k over m times x. Do you remember that? The acceleration of an oscillator. It was like the first thing we did, didn't we? We had this oscillator, and we said, what's the acceleration? And we used Hooke's law, and we used F equals ma. Yeah, remember that? And we rearranged it, and we said A is equal to minus k over m times x. Yeah. That was like the first thing we did. Well, that looks a bit like this. This is like dq by dt, d2q by dt squared, looks a bit like an A. And then there's my q is like my x. Oh, so this minus 1 over lc is a bit like my minus k over m. And we'd said before for mechanics that omega equals the square root of k over m. And that was for a wave that had that pattern, for an oscillation that had that pattern. So what I can say now is that, oh, you want to know the q in time? Then we'll have a cosine relationship, and my frequency, my natural frequency, equals 1 over the square root of square root of 1 over LC. And I don't, at this point, we don't go anywhere with it. It's just, no, you can use that analogy to get there. We're going to pick this up later on, but basically, it's basically being able to draw the analogy with mechanics for what we're doing electrostatically in this electromagnetic section. Okay. So from this chapter, know that. Know those two, yeah, that one and its body, and know those two. Okay. And have a feel for the other things. But you'll see in this next chapter, I'm going to stop now and